we'll start on the list. As Assa mentioned, so it's really a pleasure to have Assa here virtually, all the way from Israel. Assa is a very well-established physicist in our field, so he would need no introduction amongst physicists. But just nonetheless, as a general introduction also for many non-physicists amongst us. So he, as I mentioned, he's very well-established, and he worked in many different fields, and in particular, his focus was on on quantum phenomena in condensed matter systems. So he's an expert on spin system, magnetism. He actually wrote a very famous book about this. He worked in quantum Hall systems, superconductors, so-called Kondo systems, mesoscopic systems, quantum impurities, graphene, and the list goes on and on and on. And he also wrote a very nice book for non-physicists and also for physicists, which is called Maxwell Demon, which really illustrates very nicely many concepts related to thermodynamics, which he'll talk about today. So there's a really very important relation, which is continuing being explored between thermodynamics and mechanics and quantum mechanics, really fundamental, and people keep on coming back to it over and over again. So just a very, very quick biography. So he got his bachelor's in math and physics at Hebrew University, and he studied at Weizmann, and then he got his PhD at Stony Brook. We share the same advisor, former advisor, and he was a professor at Boston University. He came back to Israel, where he's been at the Technion. So ever since, he also became dean at Technion, and he was a visiting professor at Stanford and Harvard and in Paris. And so it's really a great pleasure to have him. And I wish it would be in person. And as he mentioned, of course, the news nowadays is very exciting, so it's pretty hard to compete with it. But nonetheless, we had a very good showing. So just as a general remark, so I'll mute everybody. And then if you want to ask really pertinent questions, you can unmute yourself and ask those. Otherwise, you can ask them in the chat. And then at the end of the talk, as usual, we'll come to a chat box and we'll go through the question. Of course, you can also just ask questions at the end. But if it's a very relevant question, you think people not understand, and you don't understand what's going on, if you don't ask that, please do ask it also as well. Okay, so I'll unmute everybody. I'll mute everybody, and then Assa, you can unmute yourself, and then we'll just proceed. So.
Hello, everybody. Thank you for coming. I know, as I said before, I have stiff competition from the news channels these days. So I hope that you will find this lecture entertaining as much as the news is. What I want to talk about is actually an old subject, but something that haunted me as a student when I was an undergraduate student back a few years ago. And thermodynamics was the subject that all students were most afraid of, not just in physics, but in all other sciences and chemistry. And it haunted me because I didn't really understand everything very well. It was very heavy on mathematics. It had lots of formulas and little physical intuition. So over the years, I learned to love the subject just because I taught it. And when I taught it, I found that there are very exciting aspects of thermodynamics that are even topical today in research, which I hope to pass a little bit of that to you through this talk. But the main issue in my talk is, can thermodynamics be explained without the mathematics and without the complications that I had to suffer through? And I think the answer is yes, but it has to be done through a story. And this is why I wrote this comic book that Zohar mentioned. And I'm going to use that story actually to explain the second law of thermodynamics and entropy in a way that I think is passable even to younger audiences and people without much formal education in physics. So those of you with a lot of formal education in physics will have to excuse me for explaining some simple stuff, but I'm sure that by the time I end the talk, they'll see that things are not as simple as they seem. Anyway, that's my introduction. Let me start the talk. And I'll just start with a very short clip that introduces why understanding entropy is important. And I hope you can hear the sound.
Everywhere you hear about pollution and global warming, keep reading about the world's climate change and the world's energy crisis. Is there really a crisis? Yes, it's an entropy crisis. But what is entropy?
That's the topic. The story starts in the center of the Milky Way, where there exists a massive black hole. This is true physics. In fact, the Nobel Prize this year went for experimental proof of the existence of this massive black hole. But in my story, the only purpose of this black hole is to serve as a place where we know nothing about, because no information can come out. So it is quite reasonable to assume that all the superheroes come from there, because not necessarily they do not have to obey the laws of physics, perhaps in the center of the black hole, we don't know. Anyways, that's where there's a headquarters for all living matter in the galaxy. And in that headquarters, there is a boss called Sir Bio. And he's extremely concerned about the situation on Earth, because as we know, there are serious ecological problems related to pollution, global warming, burning fossil fuels, rising CO2 levels, and so on. And all those problems are actually could be summarized by one word, and that is that entropy production is too high. And we'll explain what entropy is soon. So the fact that on the Earth, mankind and other sources of entropy production are working too hard is the reason that Sir Bio anoints this interesting fellow with a green face called Max the Demon. He anoints him to be the demon. Now, what is a demon? Well, in this story, he's a superhero, actually. He's not a bad demon. He's actually a good demon. And he has certain properties that other superheroes don't have. He's a very special superhero, and this makes it kind of an interesting superhero story. The main advantage this superhero has over human beings is that he can see atoms. He can see not just all the atoms in a liquid, he can also see their velocities and their positions at every point in time. And that's, of course, a very, very high task and a very difficult things to imagine us performing, or even a machine that we make. But it's not unreasonable that there could be some form of not living, but some form of machines that would be able to observe atoms. And in fact, we do observe atoms today with scanning technologies that exist. So this is his main advantage. He's not strong. He does not. He's not like Superman. He can't divert asteroids that come with a high momentum, and he can't violate the conservation of energy by giving a lot of energy to these asteroids and so on. He doesn't have any powers other than the power of observing. Okay, and this is the important part. Anyways, he's going to serve a very important purpose in understanding the second law and what is entropy. But before he can do anything to help Earth, he has to learn some physics. And he's sent on this mission. And his boss, Sir Bio, tells him, well, you have to learn some thermodynamics, and then you'll understand what you have to do. He doesn't know any physics because he's a superhero, and they don't need to know any physics. But in order to perform his mission, he does. And we also would learn through the story what are the laws of physics he needs to know. The people that teach him are actually the ones who taught us the basic laws of thermodynamics. And I picked the most important three characters from the history. They're not very famous to people outside of physics and outside of thermodynamics, but they are extremely important, and I'd like to give them their proper historical review. One of them, the first one is Count Rumford, the second is Sadi Carnot, and the last and most important is Ludwig Boltzmann. So they will explain to him all he needs to know, which is not very much, but enough to perform his mission of saving the world. The first notion that he has to understand is energy, and I'm even restricting myself to motion energy or kinetic energy that most kids learn in school about. Here is an example of a human cannonball that carries a lot of kinetic energy because he's moving very fast. But there's lots of examples of kinetic energy. Here's an example of a roller coaster going down the hill with very high velocity. It has a mass, it has a velocity, and the kinetic energy is simply given by the mass times the velocity squared divided by 2. For instance, if you have a kilogram flying at 40 meters per second, it will carry 800 joules, which is a unit of energy. The units don't matter. You have many different kinds of units of energy. And the only thing that matters is it's a property of a body with a mass. And that property goes with the body. And it's like the body is carrying like a banknote with the number 300 joules on it. So what is energy good for? Well, Count Rumford is the person that actually explained something about energy and heat. And I just want to give a very brief review of his extremely exciting life. Count Rumford, as you can see, was born in 1753 in a farm in Massachusetts. He was kind of poor when he grew up, but his first very smart move, career-wise, was to marry a wealthy wife, 50 years older than him, who gave him a fortune and a status to go and complete his studies in a military school. But then he spied and joined the British during the American Revolution. So he is considered an American traitor. And he defected from the Revolutionary Army, joined the British, and then he had to leave, of course, the United States, went to England, and then he climbed up the ranks of the army there and then the other administrative positions he held until he became a member of the Royal Society. He had enormous knowledge of physics, chemistry, logistics, economy, nearly everything that had to be known in those days. Using that knowledge, he went around Europe and helped princes and kings solve all kinds of problems. And the most important one was in Bavaria, where he got the title Count Rumford. Rumford actually is the town of his wife that I mentioned before, which was called Rumford before the revolution. Now it's Concord. And he carried that title, and that's how he's known by. He founded the Royal Institution, a very important institution in London where Faraday did his experiments in electromagnetism. Then he had a bit of a colorful life, carrying on a very long affair with the wife of Lavoisier, the most important French chemist, who was executed in the French Revolution, upon which Count Rumford married his wife, and that's why he's buried in Paris. An interesting epitaph is that he endowed a chair to Harvard University, a certain sum of money that is still today holding a chair in the physics department at Harvard University. And the Harvard University student body formed a Rumford Society that went to France 100 years after his death in 1922. They found his grave, and this way he was eternalized. I mean, they put up a nice tombstone on his grave, and that's why you can find his grave in Paris, and he is also memorized for his great contributions to physics. His many contributions to inventions are just mentioned here. He invented a fireplace that is well known in Britain. It holds the smoke outside of the living room and up the chimney. He invented different culinary ideas like the potato soup, thermal underwear, photometer, drip coffee pot. And anybody who visits Munich should visit the English gardens that he designed, which are extremely beautiful. And this is his grave, and this is the tombstone that was erected by the Harvard students. What was his contribution to physics? Well, he said a very simple thing. Heat is actually a form of motion energy. And that was very revolutionary, even though you think, you know, what is so deep about that? Well, before he proved that, the thought was among chemists, including Lavoisier, that we mentioned before, that heat is actually some kind of a fluid, caloric fluid that has a finite amount that the body carries, and it flows from hot to cold, like air flows from high pressure to low pressure. And this was debunked by his experiments that I draw here. So while he was in Munich, he built cannons. And he looked at the boring process of cannons, where you take energy, which is motion energy, off the lathe, and you bore a cannon. And what happens is the cannon heats up. And you can measure how much it heats, and you find that it's infinite. In other words, you can rotate this for an infinite amount of time, and the water will keep heating up more and more and more, which to his mind was a proof that heat is actually equivalent to the energy that you're investing in the boring process. He did not prove it, and he didn't really phrase it. It was done by Joule many years later using very careful thermometry, but he's credited for the thought that, in fact, energy is not getting lost when you bore a cannon, or when you stop a car, or when you have any friction. It doesn't get lost, it just turns into heat. So why are laws of physics good for? Laws of physics are good for telling you many things and solving problems in exams. But in my mind, what separates laws of physics from other laws of other sciences is that laws of physics tell you what cannot work. And sometimes to prove that something cannot work is much more difficult than to prove that something can work. And this is an example. This is a perpetuum mobile. And it looks like this should rotate because the torque coming from the extended arms is larger than the ones on the left, which are shorter arms. So the question is, can this thing really rotate? So it's not a real experiment. And the idea that this guy can go on and on without stopping, and even you can connect to it you can connect to it some load and perform work on it, means that energy is not conserved, because it started at rest and suddenly you get motion out of nothing. So getting motion or energy out of nothing is forbidden if energy is conserved. So in other words, perpetuum mobile cannot work because of the first law of thermodynamics, that energy is conserved. But on the other hand, energy can get passed around. So like money can get passed around, so it doesn't have to stay with one body. Here you can see two colliding go-karts. They have a total energy of 300 joules. After the collision, 200 joules pass from one to the other, so this one slows down, this one goes faster. The total energy, in principle, is not changing. I'm ignoring friction in this and heat. And this is conservation of energy that we all know. And you can see that energy gets passed around in many circumstances. But this is an example where a ball that has a well-defined direction and a well-defined velocity gives its energy to many other balls. And as you can see, the other balls get velocities which are quite random. I mean, they're not random for a very good pool player, but they look quite, they're obviously random when I try to make a break shot. And all these balls fly in every which way. The sum of their kinetic energies is the same as the one that we started with, but it's spread among many different balls. This is essentially what goes in friction. So sharing the energy makes the system very disordered, very disorganized, with lots of different velocities which are not pointing in the same direction. And very colloquially, we call that higher entropy. And I'll explain later more precisely what entropy is. But this is an example of how a very ordered motion of the first ball turns into a disordered motion of many balls. And that's essentially what goes on in heat. So in the experiment where they're racing down the roller coaster at very high velocity, they stop, and Max asks Rumford, what went on? I mean, we were going at a very high velocity and you told me energy is conserved. And then Rumford says, yes, but now touch the brakes. He touches the brakes, he of course gets burnt, and he says, you see, all the kinetic energy that was in our motion just went into heat. And it didn't get lost. That's how the car stopped. So if you want to look at another way of getting entropy higher and energy dispersed among many particles, you think of stirring a liquid very fast, and this way you kick a lot of molecules around, and the motion of the spoon goes into heat. And if you want to understand what does heat do to a system, well, Max can tell you. He can look at the molecules and he can tell you that these molecules are just running around in every which way in a chaotic fashion. So there's a lot of kinetic energy, but it's all very random, and that is giving those molecules that kinetic energy is giving them heat. So that was essentially the explanation that Max gets, and it's good enough to understand more or less what is heat, even though the example is for ideal gases, and of course complex systems are a bit more complicated, but essentially the same idea goes through. The second person that I mentioned before that had a very important role in thermodynamics is Sadi Carnot. And Sadi Carnot had a short life and not a very happy one. And he had two unfortunate circumstances. First, he was the son of Lazare Carnot. Lazare Carnot was very famous. He was head of logistics during the French Revolution. He was a revolutionary. But after the royalists came back, he had to go on exile to Belgium and leave his son. And that caused the career of his son, Sadi Carnot, to take a dive under the royalist regime. The other unfortunate circumstance, he was the uncle of President Sadi Carnot. And why is that unfortunate? Because if you go to Paris, you will not find an avenue or a park or a circle named after Sadi Carnot, the physicist. There's a big avenue on President Carnot, and no mention of Sadi's Carnot contribution. But in the physicist's opinion, he is definitely one of the greatest physicists that existed in that period, and responsible for the development of second law of thermodynamics. He studied under important physicists at the Polytechnique, but then he was not given an academic career, so he went to the military, where he was fascinated by steam engines. Steam engines at the time were very high-tech. They were the British advantage over the French, because the British went through the Industrial Revolution and developed steam engines and overtook the economy of France. So as a competition between Britain and France, there was a study of steam engines in France, where he published a very enticing, intriguing title called Reflections on the Emotive Power of Fire, which is a very beautiful title for understanding heat engines. This book was meant for the public. It didn't have any equations in it, lots of words, but it carried the grains of truth that, that later led to the second law of thermodynamics. His fortune went bad when he was diagnosed with some mental illness, and then he died of cholera. And that's very unfortunate for us, because they burnt all his writings, which might have contained other works of genius that we don't know about. And he's buried in Ivry-sur-Seine. I went to see the grave, and I found an interesting list of accolades on it, which reflects French hierarchy of of accolades. The first accolade is that he was a student of the École Polytechnique. So that, I guess, is a badge of honor for French that carries the most weight. The second, that he was a captain of engineering, capitaine du génie. And the third one, that he was a physicist. And the fourth one, as if as an afterthought, he was the founder of thermodynamics. And what did he say? Well, he said something that sounds interesting and not self-evident. The production of motive power is due to the transportation of heat from a warm body to a cold body. Okay, so if you reverse that sentence, it means you cannot produce any power unless you have a warm and a colder body. If you have just one warm body, it's not enough. You can't make any power engine out of a single temperature. If you put a generator on the sun, you say, oh, I have lots and lots of heat here. You won't be able to turn on a ventilator with it or produce any electricity out of it unless you have some colder body close by. So that is one of the manifestations, one of the formulations of the second law of thermodynamics. It's obscure, it's not proven, it's taken as a postulate, and it took many, many years to really understand it, and it was challenged a lot by the best physicists. And this is actually the purpose of Maxwell's Demon, if you want. So another formulation is heat can flow, but by itself, without any interference from outside, only from hot to cold. You cannot have heat going from cold to hot. And these are other less obvious consequences of the second law. So air cannot flow from low to high pressure. And that is another manifestation of the same law. We know that air flows from high pressure to low, but why can it not flow the other way? And this will violate the second law of thermodynamics. Steam engines cannot operate without cooling. That's what the Corob told us. Another one, which is a bit more difficult to show, but it's still true, you cannot cool a room by just opening a refrigerator door and hope that the same way the refrigerator cools the vegetables in the refrigerator, it will cool the whole room. It won't unless you take the heat exchanger and put it outside of the room. But that's another manifestation of the second law, and there's many others. Now, as you can see, as you go down the list here, it becomes more and more less obvious that you get all these no-no statements coming out from a single postulate, but that's what's beautiful about thermodynamics. So we'll leave it at that and show that Feynman, one of the greatest physicists of the 20th century, gave it a lot of thought, and he said, well, maybe you can actually violate the second law. Here's an example. You take a hot gas and you put a propeller inside. Now, the hot gas has all these molecules moving in every which way, as we said. So they hit the propeller in both directions, and it, in principle, can move a little bit to the left, a little bit to the right. But then you connect it to a ratchet. A ratchet only allows it to go clockwise. Okay, so what will happen? Well, if you think about it naively, you say, well, the hot gas will just bang on this propeller and will only be able to turn it clockwise. So we'll get some clockwise moving axle. We can connect it to a weight and lift it. So the question is, can it work? This is called an entropic perpetuum mobile. It will seem like we're extracting work out of a system that has one temperature. The hot gas is the same in both chambers here. It's connected. Well, the second law says it can't work. And then you have to ask, why doesn't it work? So I didn't mention before, but if you want to show without using the first law, the energy conservation, or here, the fact that you cannot operate on a single temperature, if you want to show that something doesn't work without using these laws, you have to work very, very hard. And Feynman tried actually to work very hard to prove it. And in fact, he didn't succeed. There were some other people that wrote some papers that showed it, but it's very, very difficult, believe me, to prove that this doesn't work. But the reason it doesn't work is simple. you have to cool the pole. You have to cool this, this lever that goes, because here's an example. This is the lever. Now, when it's down, it stops the ratchet from moving. So ratchet can move only to the left and lift it up, and then it'll come down. But now think of energy conservation. When it comes down, there's gravity pulling it down. It'll bounce up because energy is conserved. It can't lose its kinetic energy. There's no friction. So what will happen, it eventually starts bouncing up and down and become what you call a hot ratchet. And if it's hot, the ratchet can move in each way and the machine stops working. So that's an example. But I didn't prove to you that the ratchet doesn't work. I just showed you an argument. To prove it's very difficult, you have to calculate all the velocities and the energies and how they're distributed, and it's a topic of very high difficulty. But the reason it doesn't work, of course, is because it violates the second law of thermodynamics. You cannot extract work from a single temperature value. Okay, so you say, okay, even Feynman was convinced that the second law is correct. But Maxwell, who is one of the greatest physicists in the history of physics, he is the one who devised the Maxwell equations that solved essentially the connection between electricity and magnetism and found radiation. So he explained electricity, magnetism, radio waves, all the way from low frequencies to gamma rays, and unified them all with beautiful equations. And he also worked on thermodynamics. And here he was a bit of a skeptic. He said, I can think of some creature or some device that will violate the second law. And here is what he thought. Imagine a being whose faculties are so sharpened that he can follow every molecule in its course. Such a being, whose attributes are still essentially finite as our own, would be able to do what is impossible for us. The being is what we call Maxwell's Demon. It's some small creature that all he has to do is open and shut a door according to what he sees. So opening and shutting a door may cost energy if the door is heavy, but you can make the door as light as possible and make the friction be as small as possible with design. And this is not a physical limitation of his device. This is a technical limitation perhaps, but in principle, you could reduce the work that the demon is doing by opening and shutting a door. And once you have this demon working, he does the following. Every time he sees a hot molecule, a fast-moving molecule, he lets it through. Every time he sees a cold molecule, he lets it through from the right to left. And he separates the hot from the cold. Eventually, you get all the cold molecules on the left, the hot molecules on the right. So you get two different temperatures, because temperature is measuring essentially the average kinetic energy, and it's different. Now you have a two-temperature system with which you can extract work according to the heat engine idea, that you have two temperatures and you can make the system like a steam engine, move a locomotive or lift weights or whatever. All that was done here is this harmless, seems like, work of the demon that didn't take any energy. So there's no violation of conservation of energy. Energy is the same in these both systems. It's just the way it's separated. Here it's mixed and here it's separated. The demon does some unmixing. And the question is, once you have this demon, you can reduce entropy. This has a lower entropy than that, or you essentially can violate the second law. So where is it wrong if we believe the second law is correct? Well, it took 100 years. So during those 100 years, you have to remember, we had Einstein, Dirac, we had Rutherford, the great experimentalist, we had all the greatest physicists lived in the 20th century, and they essentially understood enormously many new things about quantum mechanics and so on. This is in the realm of classical mechanics. But the question of, is the demon possible or not possible, took a long time to answer and was only answered in the 1960s, to our surprise, as we can see in the following. But if we don't answer that question, if we don't answer, is the demon possible physically or not, we don't know if we believe the second law or not. And that's a very important statement. As we saw, the second law has lots of consequences. So during the adventures of Max the demon, he confronts Sadiq Carnot, tells him about the second law, and he says, you say that energy can only go from hot to cold. So I can think about it mechanically as a hot molecule giving some momentum and energy to a cold molecule that's slow. So eventually the hot slows down, the cold speeds up, and you can say heat has moved from hot to cold. If you think about it this way, you can think of a counterexample. In the counterexample, here are two P's. This P and this P are in 90 degrees directions. You kick this P at a very fast speed, and you kick this P at a slow speed, but they collide. According to the laws of mechanics, if you do this kind of a collision, the slow P will stop, and the fast P will be diverted a little bit and move even faster. So according to mechanics, there's no limitation to prevent you from moving energy from cold to hot, according to this particular example. Now, of course, it's a well-designed counterexample, but it's a counterexample. Seems like heat could flow from cold to hot. Question, what about the second law that says that it has to be the opposite way? So Sadiq Carnot in my story doesn't know the answer, and he has to send him to Ludwig Boltzmann. Ludwig Boltzmann, the inventor of statistical mechanics, lived at the turn of the century. Very complicated personality with some problems that he had, psychiatric or mental health problems, but he was a genius, like all the others I described before, and he essentially explained the second law. He worked on the kinetic theory of gases. He surmised that the matter is constructed of atoms before there was experimental proof. He had lots of controversies with colleagues that deteriorated his health situation, which ended in a tragic death in Duino, in North Italy. But his main contribution to physics, which actually even carries on to quantum mechanics, is that there are some laws in physics that are statistical, not deterministic. They are laws that are based on the theory of chance. And to understand the second law, you really have to understand statistics and chance. And he invented the famous formula that's on his gravestone relating entropy S to probabilities. So he explains to Max what is statistics. Now, this is a very short course in statistics that takes like a page of a cartoon book, but it really captures the most important aspect of a statistical law. A statistical law is very different from a deterministic law, because a deterministic law is when you know exactly the initial conditions or the velocity of a body, and you can predict where it's going to go according to the laws of mechanics. So he shows here, he knows exactly where this cup is going to end. He throws it very precisely, he hits the vase, and he never misses, because it's deterministic. That's a law of mechanics. And then he asks, what's a statistical law? And he says, okay, now you have to think a bit about gambling. So a statistical law is a law which, if you do a single experiment, you don't know what its result is going to be. For instance, if you flip a coin, you don't know if it's going to be heads or tails. Let's say the coin is fair, so it's 50-50% chance. Now, how do you use a statistical law in physics where you want to predict things? Well, apparently you can if you repeat the experiment many times. So he's flipping the coin, and every time he gets heads, he puts it on one side. Every time he gets tails, he puts it on the other side. And he watches what happens. In the beginning, you don't know what's going to happen. Some coins get here, some coins get to be here, and the scale is tilting back and forth. What is nice about statistics is that if you keep doing it for a long time, you know with absolute certainty that the scales is going to come closer and closer to equal to balanced. This is how you get essentially certainty out of uncertainty. It's not that any experiment you can predict, but the fact you have many, many experiments and they all governed by the same laws means that you can predict what will happen after you take many, many coins and flip them. There's going to be a balanced scale. Of course, you have to do an infinite number to be absolutely balanced, but if you give it like some margin of error, then you can estimate with high precision when it's going to get to be balanced. And this is quite magical, but out of uncertainty, you get certainty. But this is the basic truth that governs thermodynamics. Why? Because thermodynamics is a theory of many, many atoms. And he gives some interesting examples based on an aquarium with 4 fish. So the game is the following. You have 4 fish moving around. It's like atoms in gas. You don't know where they're going to go. They're not very collaborative fish or smart fish. They just move around randomly. And you put a divider and ask how many fish are going to be caught on the left and on the right. And you do the experiment many times and you plot what's called the histogram. So there's going to be one case where all the fish are on the right and one case where all the fish are on the left. And then there's going to be lots of cases where 2 fish are on the left, 2 fish are on the right. Now, if I just want to say how many fish are on the left and right and not care about which fish, then you see that the largest number of circumstances, or what's called microstates, is on the equipartition, equal distribution of the 2 fish on both sides. Now, of course, there's a big chance also of finding 3 and 1. It's not negligible. If you want to gamble, of course, you'll gamble on the highest column because there's the maximum number of possibilities here. And that's the highest probability. For any gambler knows that if you have the highest number of possibilities, that's the highest probability of winning. But it's not so convincing that with 4 fish, you should always gamble on 2-2 because the numbers are not large. But let's see what happens if you use more fish. Now, by the way, the height of the column is essentially a measure of the entropy. So as you can see, entropy is large when you have the maximum amount of possibilities, and therefore the least amount of certainty of which fish goes where, right? Which is opposite to here, where all the fish are here, so you know that all the fish are here. The red could be here, the red could be on the right, and so on. There's a lot of uncertainty here. So uncertainty is related to entropy and to probability. Entropy wants to grow. Let's see why. So if you take 52 fish and you do the same histogram I showed before, the numbers are slightly different. The equipartition of 26 fish on the left and right have, if you look here and you can see the writing, it's around 500 trillion microstates, while all the fish on the right or left is only 1. So 500 trillion versus 1 is convincing. You should not gamble on anything besides equipartition if you're a clever gambler. Now, if a system is not in equipartition, let's say the system is here, let's say you have 20 and whatever is left on the other side, then you're sitting on a column which is much smaller, and if you open the gate, you should again gamble on equipartition because the system will just find where there's most number of microstates. This is exactly what happens when you release a valve and you allow air to flow from high pressure to low pressure. So at this side, if you put all the gas and you open the lever, you know that the gas will flow and will have essentially the same number of, not the same exactly, but will have the same density or the same pressure on both sides. You ask why? You ask many people in the street, or maybe some of you might have thought about it themselves, you would say, oh, the air will flow because there's a pressure and it's pushing the molecules from the high pressure to the low pressure, and then it equilibrates because the pressure is the same. But that's not the correct answer because these molecules in an ideal gas don't see any forces on them. They don't know, each molecule doesn't know that it's in the region of high density or low density. But the reason the gas actually flows from high to low is because there's many, many more possibilities for the gas to be distributed among the two sides at equipartition relative to not. So here's a number for you. There's for a 1% difference in the numbers of molecules on the right and left, or for the pressures on the right and left, for 1% only, the chance of finding the system in that situation is 1 to 10 to the power, and there's like 23 zeros here. So I wouldn't gamble that the gas will have a 1% difference in pressure between the two sides, even though it could. So this is the law of large numbers. That's why thermodynamics is all about statistics of large numbers, and those have new laws of physics attached to them, and the one we're interested in is the second law. So the second law says that it's true that you could find a system here where the pressures are not the same, and the same goes with temperature, but after a while, the system will equilibrate and will reach equal temperatures, equal pressures, and equal densities because of the law of large numbers. So it's chance that governs the laws of physics here. And the entropy, as we said, is very likely to grow because there's much more probability of finding a system at high entropy, and very unlikely to diminish. Okay, once Max understood this, he had to do some work. So he had to get an idea. Now he got the idea from a place called the Hbac Affair. The Hbac Affair is a place where physicists have a happy hour where they get cheaper drinks relative to other customers. And he sees a doorman that selects the people coming in, and he doesn't allow people who are better dressed, perhaps not physicists, to enter the bar at happy hour. And that gives Max an idea. And the idea for Hbac Affair comes from the graduate student cafeteria at the physics department at Technion, where you can see them having a reduced price coffee during coffee time. Anyways, getting the idea that he can select using his amazing powers of observation, he does exactly what Maxwell Demon did in the story of Maxwell. But in this case, he does something even simpler than what Maxwell asked. He's just opening and shutting a door and letting molecules on his side pass through, and not letting molecules on the other side come back. Now you can see all his efforts is just moving this very simple door, not spending any energy on it. This door is frictionless. Of course, you can ask, how did it become so small? That's a side story. That's not physical, but that's somehow he is able to become small and do this. But all he's doing, as you can see, is just looking and opening and shutting at the right times the door. With this, he's able to pump gas from low pressure to high pressure. And by that, he's able to operate a generator, essentially a power plant, because from the high pressure, you send the gas into a turbine, the turbine turns around, creates electricity, turns on the light, and then the gas comes back, and it has to be reheated with tap water, and then tap water gives the cold gas back its room temperature heat. Of course, you get free ice out of that. And this is a very strange power plant, because this power plant essentially works only on tap water without any investment of work, will produce electricity. So look what violating the second law does. Why does it violate the second law? Because he's taking tap water temperature and he's single temperature scale, and he's extracting work out of it. And in fact, moving energy from the tap water to a much hotter lamp, which is of course opposite to what the second law allows. So this motion of opening and shutting a shutter does very strange things to this power plant and produces free electricity, free ice, without any consumption of energy from the fossil fuels or whatever. So that's essentially what he did, and that was supposed to provide clean energy and so on to the world. But the story becomes a bit more complicated because, as usual, when you have a good idea, some evil people want to take advantage of that idea. This is the state that exists somewhere in the world. It's called Ergodistan. It has an evil general that wants to use the same idea, but for bad purposes. He essentially wants to use mechanical demons that open and shut shutters to separate uranium-235 from uranium-238. And as you know, U-235 is fissionable material to make nuclear bombs, and U-238 is not. And by observing which is the larger molecule, which is the larger atom, these mechanical demons separate between the two. This separation, unmixing again, is a reducing entropy. The question was, okay, once they have it, what are they going to do with it? Well, they're going to make nuclear weapons to threaten all their neighbors. But look what happened. They were very happy about the operation. They were saying, hooray for the nukes, long live our glorious president. No pun intended for the current election. And then down with entropy, which is, down with the second law. But look what happened. The whole facility starts catching fire and eventually exploding. That is something that annoys Sir Bio, who is watching everything. And he's essentially very angry about, oh, is this sign that I need to stop? Or okay. Okay. So I'll hurry up. He's very angry about that. So why? Because he told Max the following. I didn't tell you that, but he told him when he started out his mission, look, unlike the previous superheroes I sent to Earth that violated laws of physics and caused people to doubt the laws of physics and also believe in superstitions, and new kinds of cults and religions came out and caused some social problems, here I want you not to violate any law of physics in public. And seeing this explosion, he says, well, Max really didn't obey me. He violated some laws in public and he has to come back. But you see, Max doesn't understand, and I think the reader doesn't understand, what was really wrong with his performance and with his mechanical demons. Why did the mechanical demons not work? They did exactly what he does. Those robots did exactly what I do. And he's very upset and he doesn't understand. And then to the rescue comes Richard Feynman. I don't know how many of you have read his books. He's an amazing storyteller and entertainer and a great physicist. And he actually gave a talk that I heard when I was a young postdoc about the Maxwell Demon and the entropy of erasure. Entropy of erasure is something that came out of computer science and physics by these great physicists. It was about logically reversible computing. Now, you know that studies of computing and quantum computing are very, very hot these days. There's a lot of technology and development in this area. And it started by Feynman's interest in the processes at which we lose information by erasure, which necessarily creates heat. So this is the work of these guys, and it was done, as you can see, around, well, it's not written here, it's around 1960. So he explains to Max. He says, look, what they did in this plant was to store all the information of these cameras, these robots, in some big memory bank. And the big memory bank carried zeros and ones. Once the memory bank got filled, you had to erase those memory banks to make room for more, because there's trillions of numbers coming in, and you needed to erase memory. But erasing memory, as Bennett and Landau and Feynman showed, will produce heat. And that heat is the heat that made the plant catch on fire. So he says, I can see trillions and trillions of atoms, but I don't feel my brain heating up at all. That's what Maxwell Demon says. But he says, that's because you're Maxwell Demon. You're not bound by the laws of physics. You can reduce entropy and break the second law with your infinite memory. So now we understand that he's a demon. He's not a physical being, because he can store infinite amount of memory without erasing. If he was erasing them, forgetting them, he would heat up. And once he heated up, the machine won't work because you need somebody to cool him, and then you have again a two-temperature system that is required for the second law. So he says that's why you could operate that funny power plant, because you didn't need any cooling. And a mechanical system needs cooling, a computer needs cooling, and so on. This was the resolution which related the second law to information theory. And at this point, the story gets into some kind of a conundrum, because Hbac doesn't allow him to break the second law in public. So he's not really allowed to use his power to help the Earth. So how are we going to help the Earth to reduce entropy? I'll give you a spoiler. The end of the story is that there was an improvement in the Earth's ecological, environmental, and pollution situation. And Max had something to do with it. And he was put on trial, as you can see here. And he was accused of violating this law of violating a law of physics in public. And he said, no, I did not. And he gave an argument. And the question is, well, you'll have to read the ending of the story and decide for yourself, is his argument convincing or not? I think it's a bit difficult to decide whether he's absolutely right or not, but that's the end of the story, and it gives you some extra room for thinking about it. So that's the storybook. I just have to mention that there are really ongoing research on Maxwell Demon, information of erasure of information and heat, and Landauer's principle I discussed before, that are published even within the scientific literature these days, and especially important in the context of quantum information, which is a subject of a different lecture. So the book itself got quite nice reviews. I especially appreciate the review from Duncan Haldane, who won at the same year he won the Nobel Physics Nobel Prize, and some other authors you might know. But basically, I believe that the book could be entertaining and useful for younger audiences. You can see here some pictures of readers and people. And if you are interested in getting a copy for yourself, then you can just go online on the maxthedemon.com. And if you want a 30% discount, use the Washington University WUSL code, and it will be shipped to you. And that's essentially all I have to say. This is myself and the illustrator, Dick Coder, who is a very fine cartoonist who also draws political cartoons, if you're interested. And now I'd be very happy to answer questions, take questions of anybody who is interested in asking. So thank you very much.
Thank you very much, Assa. So a fantastic lecture. So any questions?
Excuse me, I don't have a question, but Biden won. He's up to 284 electoral votes. Exhale. Thank you.
Thank you for the update. So it's a sort of historic lecture.
Is that
maybe because of Max the Demon, maybe it helped.
Absolutely.
Any questions? Anybody? So, I mean, this is a quite sophisticated subject, which was really made very lucid by Assa. So, so it's really hard to understand many of these concepts. So, if you have any questions, or please do ask.
Well, maybe it would be appropriate to say a few words, a little bit more about, you know, the understanding we now have of entropy as information, and sort of how we view it as moderns.
Right. So there was a part of the talk that I give to students that actually shows that there is an exact equality between the what's called the entropy of information that was invented by Shannon. Now, what that entropy was invented to do was to give a value to how much information you get when somebody tells you the result of a random event. For instance, if you have a coin that you toss and you a priori don't know what it's going to be, you have essentially two possibilities. The entropy that exists, entropy of information at this point, is logarithm of 2. Logarithm is just counting, let's say on the basis of 10, it's counting the digits, some proportional to 2. But once you know that it's heads, there's only one possibility. It becomes log of 1, which is 0. So the difference between the Shannon entropy before and after is the information you received. You received essentially log 2 information from the knowledge of the outcome of the experiment, of the gamble. So the Shannon entropy tells you how much usefulness there is in a message that you get. If somebody gives you a message which is not useful, then you say I have 0 information. Or you can phrase it in a mathematical way as before the message you have some distribution of possibilities, and after the message you have the same distribution of possibilities, so you didn't learn anything, and therefore the entropy before and after was the same, the difference is 0. But on the other hand, if in the beginning you had many possibilities and after the election you have only 1, then you have received information which is log of the number of possibilities you had before divided by the number that you have after, which is the information content. Now, the same formula holds for the physical entropy of a system. It's again the log of the number of microstates, which are possibilities. I mean, you saw the fish. It's essentially possibilities of having the fish here or there, or the molecules on the right and the left. So it's very, very similar. In fact, it's the same. So physical entropy and entropy of information is exactly the same, and therefore it's interchangeable. If you have a system where you know about its degrees of freedom, or about its positions and about its parameters, and it's not completely uncertain, the system has lower entropy. That's, for instance, a situation where you know that there's 15 molecules on the right and 0 on the left. After you release the lever and they start mixing, you lose that information. So you lose information, you gain entropy. This is exactly the same. And now that we're looking at systems which are very small, with small number of degrees of freedom, it becomes actually very important to relate the two. That's what the people who are doing experiments in small systems of cold atoms or spins or electrons in semiconductors, they really can count the number of possibilities because these systems are so small, and they can relate the difference before and after a measurement to the difference in that entropy, and that entropy can be translated to thermodynamic quantities like heat and temperature and so on. I hope it answered your question, but yeah.
I have a question, Assa. How are you doing?
Yeah, great.
So by the way, I enjoy your book very much.
Thanks.
Read it some time ago, when you published it, I enjoyed it very much. So I would like to know if you can comment a little bit about the Gibbs Paradox and these ideas about, principle of indiscernible second law and this kind of, indistinguishability and things like that. What can you say? What are your thoughts about that?
The Gibbs paradox is very interesting, actually. It's a classical paradox. Okay, some people say you need quantum mechanics for it. but they're wrong. It's a classical paradox. It's actually not so much of a paradox. It's a question of definitions. Okay, I don't know if I'm not boring people who are not familiar with the Gibbs paradox, but the Gibbs paradox says that when you count different possibilities of atoms being in one place or the other, one side of the system or the other, you should divide by all the permutations of their identities. In other words, those atoms may carry some identity. You can call one atom Joe and the other one David, and so on. And there's many possibilities of having them in different places. Once Joe is on the left, David is on the right. But if it's the same kind of atoms, you should not consider them as a different microstate. Now, that is a definition that allows you to ignore their identity, which even in classical mechanics becomes useful when you do experiments that you take in and out atoms from the system and you don't care what is the identity of the atom you took out. You care that a water molecule came out. You don't care what its name was, even though in principle you could attach a name to that molecule. But if you want to work in chemistry and in physics without bothering about the names of the particles, you have to essentially associate all the different permutations of their names as one possibility. And then you can work with that and define what's called a chemical potential. You will not be able to define a chemical potential, which is the average free energy of, sorry for the words, average energy of putting a molecule into a system or taking it out, if you assigned identity to those molecules, because you don't care. If the molecules with different identities had different physical properties, like for instance, if you had two different kinds of isotopes of hydrogen, then you would have to not symmetrize or not treat them as identical if they had slightly different energies. But if you can't measure any difference in energy, you should not define different microstates according to their identity, and that's the resolving the big. That's why Gibbs had to introduce his 1 over n factorial factor. It's nothing to do with quantum mechanics that some people think has to do with indistinguishability of elementary particles. That's much a higher level statement.
Right, there were a few questions also in the chat. There was one from Paul. I'm not sure if Paul, if you want to ask it yourself or I should just read it out. So I guess you can read it. So has it been demonstrated the ratio of entropy is necessary to resolve a paradox?
No, again, I didn't hear the question again.
So has it been demonstrated that the ratio of entropy is necessary sufficient to resolve a paradox that you described?
Well, there are papers saying that, and I think they're right. I mean, I think, well, it's very difficult to measure heat at a very low level of energies. You know, energy resolution must be very, very high to measure the difference in heat. But it's nearly a tautology. In other words, yeah, I think people will say that it's been proven, not proven. You can never prove anything experimentally. You can only disprove. But it was confirmed that it's consistent with experiments, that there is a lower limit on how much heat is generated when you do an irreversible computing or when you erase a bit. Because, okay, so the original argument of Landau was actually based on a device, a semiconducting device that can have a 0 or 1, like a computer memory chip. And when you want to erase it, you had to essentially, you know, lift the double well one higher, and the ball rolls to the place you call 0, and you want it to roll and not come back, so you have to put some friction, and that will produce heat, and the minimum amount of heat that you produce is this log2 entropy that was described.
Hi, this is Paul who asked the question. If I could clarify, the question is not whether there is entropy associated with erasure or entropy increase, but whether that increase of entropy has been shown to be what resolves the paradox. I mean, it seems like it's kind of assumed that, well, we've got some missing entropy and erasure produces entropy, so that must be what it is. Has it actually been shown that the erasure is necessarily enough to resolve the paradox?
Yes, let me, okay, just a second. Okay, so I did not include those transparencies here, but the point is the following. There was a Maxwell Demon engine by Szilard. Szilard was a very important Hungarian physicist who worked on the Manhattan Project. Oh, I think he worked on Manhattan Project. Anyways, he was wondering of what could be the smallest amount of energy produced by a Maxwell Demon, and he found that precisely it's going to be T log 2. So he showed it by having a cylinder with one molecule and one division, and you put the molecule at random at one place, and without knowing where the molecule is, you won't be able to know where the piston wants to move left or right. So you can't extract useful work out of it, because one time it'll go left and the other time it'll go right. On the average, it'll give you no work. But if you had a Maxwell Demon, it will tell you that the molecule is on the right. Now you can connect the piston to the right direction and lift the weight according to the essentially ideal gas law, PV equal to 1 times T. And when you do the integral to get the amount of work, you get exactly temperature times log 2, which is temperature times the entropy change. That's in thermodynamics, is the work you get from a isothermal expansion. And that is exactly equal to T times the amount of information, Shannon entropy information, the demon extracted by reducing 2 possibilities to 1. Okay, so that direction shows that the Maxwell Demon really extracts that information. If you reverse the argument, you'll get the opposite, that if you lose that information, you essentially increase the entropy by log 2. And that entropy log 2 will give you a heat T, temperature times log 2, that you have to get rid of in order to make the system work. So it works both ways, the entropy erasure and the entropy accumulation information that the demon gets exactly equal, in the limit, of course, of no friction and most ideal circumstances. In real circumstances, I have to emphasize to all the audience, in real circumstances, of course, in order to erase a bit of memory, you have to get rid of heat, which is many orders of magnitude larger than this limit that Feynman was discussing. So we're not really in that position in a real computer, but in these experiments of cold atoms, they already reached that limit. So
actually, Killer Murch, our department, they gave a lecture a few weeks ago, also actually looks at quantum thermodynamics. So actually, there's another question by Hila. So is information related to Bayes' theorem? So the relation between information
to, sorry?
To Bayes' theorem, the relation between.
I'm not sure I know what that is. Yeah, some terminology from statistics that I'm not familiar with.
For conditional probabilities, exactly, yeah. For
conditional probability, yeah, it's so the ratio of 2, the difference of 2 entropy is like the ratio of 2 probabilities, right? The log of the ratio of 2 probabilities. So yes, so that is strongly related to the entropy of information. So when you change probabilities, it comes from information, right? If somebody is cheating in cards, and he's telling you, you know, the other guy has 2 aces, that reduces the possible cards that he has and gives you information. You measure it essentially by how much the probability distribution has changed by that message, right? It goes all the way from complete uncertainty to absolute certainty. Okay, so this is the common use of entropy, information entropy.
Thank you much. So actually, we have 2 more questions. I mean, so one in the chat. So by David, I'm not sure if you want to ask it yourself, David. So are you able to predict information overload for experiments, for given experiments?
Can you explain what
Are you
information?
able to predict information overload for given experiments?
What is an information overload? I don't understand what is an.
Yeah, I mean, David, did you want to specify? David, you can unmute yourself if you're. I guess in the meantime we can go. So Leon has a question.
Yeah, my question is, if entropy inexorably continues to increase in the cosmos, does it ever reach a maximum? And if so, would it be at a stable or a uniform temperature that would be the same everywhere in the cosmos?
Okay, that's a hard question that I don't know the answer to, because I don't know exactly. I'm not a cosmologist. I don't know what the predicted history of the cosmos is supposed to be, because the cosmos is not, as far as I understand, a closed thermodynamic system that reaches equilibrium. It's a system that is flowing from some initial condition to whatever future that the cosmologists tell us it goes to. And ever since the Big Bang, a little bit after the Big Bang, when the system seemed to be in equilibrium, after the inflation, the different parts of the system don't talk to each other anymore, or don't interact strongly enough to describe equilibrium. Now, equilibrium in thermodynamics is a process that is reached by lots and lots of collisions and chaotic motion of the particles with respect to one another. And I'm not sure that you can apply those laws to the evolution of galaxies and so on, which are very far from each other and interact very weakly. I know that astrophysicists use some aspects of thermodynamics in their equations, but they can't use all of it because, again, the conditions are not satisfied for systems which are flowing and not in equilibrium.
Thank you.
So there's another question by Frank. I'm not sure, Frank, if you want to ask it yourself in the chat. If so, you can unmute yourself.
Oh, okay, sure. So if you have uranium-238 and 235 and you separate them by effusion, you have them in a container and the gas molecules, and they effuse out through a little hole. And so the uranium-235, the uranium hexafluoride 235 will effuse faster. So you can separate those two. So could you relate that to the concepts that you talked about, please?
Yes. You are able to separate and you are able to move gas from one place to another, but you have to invest a lot of energy. You have to come from the outside and invest a lot of force through centrifuges to essentially overcome their entropic tendency of mixing by putting an external force on the system, which is what you do in a refrigerator and in other systems that you drive locally to reduce the entropy. Of course, globally, the entropy will increase, but locally, you can separate materials. And in fact, there's many ways of electrolysis separates, different parts of molecules from each other by putting a very strong electric field. So I think the separation in centrifuges is a similar idea. You use essentially a centrifugal force to separate, to give them essentially different chemical potentials, and they will occupy different parts of the system because of that. What the Maxwell Demon did is do all that without any forces. He just moved shutters back and forth and seemingly got it on the cheap, which of course didn't work. But it's just because it's a story, of course. It's not really not a realistic suggestion for separation.
Thank you. That sounds consistent to me with what I know.
Okay, thanks.
Sure, question. There's another question by Joe. Joe, do you want to ask the question? Joe? Okay. Other questions anybody has? Anybody else has? Okay, so I mean, so let's.
Am I there
sorry,
now?
sorry.
Can you hear me now?
I can barely hear.
Can you hear me now?
Yeah, now I can hear you.
Yeah, I can hear you.
Okay, sorry about that. My audio was set up wrong. Assa, I appreciate your talk. Thank you. You sound like the right person to ask this question. It's kind of an advanced topic. Have you heard of Tassalus entropy? Tassallis?
Yeah. It's Tassalus entropy, exactly. Yeah.
Right. It's an entropy defined with a different functional form than the Boltzmann entropy.
Yes, and it's he argues that it's a more general form and that it can be used for more stuff. And he says that he's derived it for theoretical purposes in some cases, but some people just call it fancy curve fitting. Do you know anything about it? What's the current beliefs in it? Pro or con?
I'm very ignorant of Tassalus entropy. I heard the words and I saw some papers using it. It's a definition. You can always define functions, functional forms, and see if you work with them, they are useful. But I'm not at all familiar with where they have been applied to solve any physical problem that I know. Some of the entropies defined in the literature are used to do numerics when it's difficult to compute the real entropy. So it's a proxy. It's like easier to compute and has similar properties. But I'm not sure about Tassalus entropy at all. And I'm sorry, I can't answer your question very well.
Well, that's okay. I mean, I asked the question multiple times and I've kind of gotten that same answer. So not a lot of people have dealt with it.
Okay. I'm not saying it's not useful. I just don't know.
Okay. Thank you. Appreciate the talk.
Yeah, thanks.
So other questions? So lots of people thank you for your presentation. Okay, I guess, and one of the mentions that Paul already mentioned, the book looks great. So really, thank you very much, Assa. I'm sorry we can't do it in person. Hopefully, oh, sorry, there's one more message. Oh, okay, yeah. Gerardo was mentioning it's non-additive. And entropy is entropy is non-additive. Charles entropy is non-additive. So thank you very much, Assa. It was a really great presentation.
My pleasure. Thank you all for coming. Good luck with the rest of the election.
Well, thank you. Okay,
congratulate me. My prediction was correct.
Oh.
Okay.
Long time before, eh?
So I'll stop the recording.